Okay, so to wrap up section 12.4, we're going to go over something called the power rule. Power rule is a nice little shortcut to finding derivatives. So we won't have to really use limits anymore. We'll use some algebra skills, and it actually kind of simplifies the process quite a bit, which you'll probably appreciate. Okay, so notation for the derivative, aka or also known as, right, the tangent slope is what the derivative is. So here's the ways we denote this. So for the derivative, we got f with this little asterisk x, read f prime of x. Okay, we can also write this, and this is kind of the new part, as y prime. Or sometimes is also represented as dy over dx. D stands for delta, meaning change in y over change of x. For the most part, we won't use that a whole lot, but maybe if you take calculus next year, you'll see that more. We'll just stick with f prime and y prime for the most part, okay? Okay, so here's a rule for a constant. For example, if we have y equals 3 or f of x equals 3, we know it's a horizontal line. Okay, so what's the slope of a tangent line to a linear equation? Well, we know with linear equations, the tangent line is going to be the same line. So what's the slope of this horizontal line? It's 0. Okay, so if we have f of x equals 3, the derivative of that will always be 0, no matter what constant this number is. Okay, I put here in words, tangent line will also be horizontal. All right, so the rule is this. If f of x equals c, some constant, then the derivative of this will always be 0. Okay? Okay, we don't really need the constant multiple rule because the power rule takes care of it, so we're going to focus on the power rule. Here's what the power rule says, and this is kind of the big shortcut for derivatives. Write this down. If f of x equals a times x to the n, a and n have to be real numbers, which they will for most of the problems that we're going to be presented with. But so I guess you could skip writing that down if you want to. This is the important part. Here's how you find the derivative of a single term. We take whatever the exponent is and we bring it out front and multiply it by the coefficient that's there. Okay, and then we reduce the power by 1. We subtract 1 from whatever number that is. And that instantly gives us the derivative. Okay, so here let me demonstrate this over here. Let's just say the function is 5x to the 8th. Okay, so what we do is we take that exponent of n, okay, we put it out front, multiply it by the 5, and then we reduce the exponent by 1. So the derivative is 40x to the 7th. Without going through the whole limit definition, we can get it right away with the power rule. Okay, so that would be the answer for that. All right, now the sum and difference rule just means this is just a single term, but what if I had like 5x to the 8th plus 2x squared and other terms? Well, you just kind of handle them separately and add them together. So if I had multiple terms, I continue that power rule for each individual term separately. So that's all this means. So if we have a function that has like g of x plus h of x, or subtracting, to find the derivative, we just find the derivative of these terms individually using the power rule. Okay? So you'll see that in the examples to follow. Okay, so let me demonstrate number 1 and 2 for you. So we're going to use the sum and difference rule right away. I have two terms, but we're just going to use the power rule separately for both of them. You may even want to write the exponent in here when it's not there. So f prime, or the derivative, will be equal to, the power rule says I take n and I put it out front. So I have 1 times 2x, and I'm supposed to reduce the exponent by 1. So that gives me 2x to the 0. Okay, what about constants? Constants, it's always 0. Okay, so the derivative of this term is just going to be 0. So minus or plus 0, doesn't matter. We're going to drop that anyways. So what does this simplify to? Well, anything to the 0 power is 1, as you recall. Right? So we end up with 1 times 2. Okay? And then we're just subtracting 0. So there's the derivative. It's just 2. It takes a little while to get used to. Let's take a look at number 2. Again, we're using the sum and difference rule, but we're just going to treat both of these separately and do the power rule separately. This one has y, so I'll use y prime to denote it. Exponent comes out front, 2 times 3x, and then we're supposed to subtract this by 1. So it's now x to the first power. Okay, let's do it again for this term. I have an exponent of 1 right now, so minus 1 times x, and then I got to reduce that by 1. Okay, so we saw both of these exponents go down. 2 to 1 and then 1 to 0. And now let's just simplify it for our answer. So y prime will be equal to 6x. And then again, we have anything to 0 is 1. So 1 times 1 is 1. So we get y prime is 6x minus 1. Okay, go ahead, pause and try number 3. All right, here's your feedback on 3. So we got the 4 comes out front times the 10, reduce it down to x to the third. 2 times the 5, reduce it down to x to the first, and then we got the constant rule, 0. So here's the final answer for number 3. Okay, for the problems below, let's add a little success criteria up top here. Let you write this in. For rational and radical expressions, which are coming right up in the next few examples, convert to exponential form to find the derivative, to find f prime. Okay, then when done, with the power rule, because we're going to use that again. So when done with the power rule, convert back to original form. All right, here's just the reminder you need on some of these properties. When we have, a to the x negative n, remember that the negative exponent is supposed to go in the other part of the fraction. So we do something like this. X to the negative n by itself is 1 over x to the n, but if you have a coefficient here, it stays up there. Just this part moves. Okay, also the radical part, if we have x raised to the a with root b, we convert this, the root always goes in the denominator. So we say a over b is how we convert that to exponential form. Okay, so here we go. We've got a rational expression, rational meaning fractional expression. So let's write this first as 3 times x to the negative second. Okay, you kind of want to get it in that polynomial form so we can, make it look like this so that now we can use the power rule. That's the idea. So now we're ready for f prime. So f prime of x will be negative 2 times 3 times x. Now be careful here. When we subtract 1, right, it's going to be negative 3. Make sure you take that in the right direction. Okay. Okay, and then we got to convert it back to its original form when we get our final answer. So when done with the power rule, get it back to how it started, and it was a rational function to start. Okay, so the answer is going to be, we get -6 here, and then the x cubed goes on the bottom. If you're not sure really what's happening, remember we have -6 over 1 basically times 1 over x cubed, if that helps. So the -6 times 1 stays up here. And there's the derivative. Okay, try that for number 5. Okay, here's 5. So 7 times x to the -1. Multiply, reduce that, subtract 1 from it. Here's the answer. Or you can put the negative with the 7 or out front. Doesn't really matter. Okay, let me show you these radical ones. Let me take you through 8 and 9 and then wrap it up, let you try 6 and 7. Okay, so here's what we need to do for the radical expression. Put it into exponential form first. So remember, the root goes in the denominator, and here we have x to the first inside. Put the 1 in there if that helps. So you have x to the 1/3. Okay, so here's the derivative for this. 1/3 times x, and then we got to subtract 1 from that, right? So the math on that is 1/3 take away 1. So I would write 1 as 3 over 3. So if you're going to take 1/3 and subtract 1 from it, why don't you write it as 3 over 3? So now I've got 1 take away 3 is -2/3. Okay, so that's what we have here for an exponent. All right, so 2 things need to happen now. That's a negative exponent, so we should put it in the denominator to take care of that. So this is 1/3 times 1 over x to the 2/3. And then this started in radical form. So let's convert it back to radical form to finish. So the derivative is, up top we have 1. On the bottom we have 3 times the cube root of x squared. Okay. All right, let me show you 9. 9, we need a little more room, so I'm going to scoot it over a little bit. Okay, so I'm going to put this in exponential form. So we get 8. Remember, this is a square root, so if it's not there, that can be tricky. Maybe write 2 in there if you want. So I have 8x raised to the 5/2 plus 2 times x raised to the 3/4. Okay, we've got some fraction work again to do, so now we can take the derivative. So we have 5/2 times 8. Maybe I'll just put 8 over 1 if you want to get them lined up. And then x, I'm supposed to take away 1 from this. So if I have 5/2, take away 1, so that'd be 2 over 2, so that gives me 3/2. Use your calculator if you really need help with that. But that's what we get. Plus, I have 3/4 times 2. And then I've got to take 3/4 and subtract 1 from that. So if I subtract 1 from that, we're down below 0. On the number line, we're going to have -1/4 for that. Okay, so here's going to be the final answer. Let's see, this is 40 divided by 2, so that's 20. Convert this to a radical. So this is going to be square root of x cubed. Okay, well, that next term, let's see, that's going to be what, 6/4? 6/4 reduces to 3/2. And then we can change this to the 4th root, but it's supposed to be in the denominator. Or maybe you want to see it like this first, I don't know. 1 over x to the 1/4. Okay, so now I have 3 on top and 2 times the 4th root. I don't have much room, so I'm just going to erase it and put the final answer. So 3 over 2 times the 4th root. They don't get much messier than that one. That is a tough one. Okay, try number 6 and 7.